Okay, we're going to finish up this last chapter. We're going to talk about that'll be it, I think. All right. So we are on carbohydrates. And last time we talked about carbohydrates and sort of their couple of characteristics of it and just molecules in general. We did talk about chiral molecules, and chiral molecules typically will have a chiral carbon, it is sometimes referred to. And a chiral carbon is basically a carbon that has four different groups attached to it. Now, one of the things about a chiral compound is if you take that compound and you stick it in front of a mirror, although my drawing here is probably not the best drawing to represent that. Um, The mirror image is non-superimposable. So the mirror image is non-superimposable. And that is because really it has those different groups attached. And basically, there will always be some type of group that's attached to that carbon, for example, that even if you try to rotate it around, because of the angle, it will really always be off. So the example that we sort of saw as a common example is, again, your hands. If you put your hand in the mirror, you got your other hand staring at you. And again, if you pull it out, you can rotate it around, get certain things to line up, like your thumbs. But again, palm up and palm down won't match, and you just won't get everything to match perfectly. And that's different than an achiral molecule. And an achiral molecule, basically the mirror image will superimpose. And basically the idea there is you don't have four different groups attached to that carbon. So it will basically allow really two groups to sort of line up nicely, and the other groups will line up as well with some rotation. Now, when we talk about carbohydrates, they obviously are made up of carbons, hydrogens, and oxygens. And really, most monosaccharides will have one of two sort of groups up on top or near the top. And one group is basically our aldehyde group. And again, these are what are sometimes referred to as aldoses. And again, it basically has the aldehyde group attached. We can also count our carbohydrate or monosaccharide based on how many carbons there are. And everywhere it sort of intersects there is a carbon, a chirocarbon actually. And again, we could count it up. So like 1, 2, 3, 4, and 5. And that would be what's referred to as a pentose. There's also obviously a triose, a tetrose, which is 3 and 4, and a hexose, which is 6. So that's some ways we classify it. Now, the other sort of organic group, really, which is what it is that you'll find towards the top of the compound, is really a ketone group. And it is really just like our kind of ketone group we had in organic chemistry as well. You basically will have your 3-carbon run. And again, you'll have your carbonyl carbon there with your carbon oxygen double bond, just like you find in organic chemistry. As we talked about, just like in organic chemistry, this guy will always be this group here because of that hydrogen will always be at the end of the carbohydrate. That's a very last carbon is where you'll have that carbon oxygen double bond. Here, because it's a ketone, and again, you need that 3-carbon run, you will always have that sort of carbon oxygen double bond, most likely on the second carbon down because of that. This is obviously what is referred to as a ketose, and you also can identify it based on how many carbons that it has. Now, monosaccharides like glucose, fructose, and so forth, they will also turn themselves into cyclic structures, and they'll basically close up the ring on itself and basically make a cyclic structure. So what they will typically do is make one of two sort of cyclic rings. They'll make one that looks like a cyclohexane ring, except that it does have an oxygen inserted inside, which means basically it's a 5-carbon ring rather than a 6, because it has that oxygen inside. And they will also make one that's very similar to cyclopentane, also short 1-carbon because the oxygen gets inserted in there, and that is going to be a 4-carbon sort of ring. So when we turn these guys into cyclic sort of structures, and they do oftentimes kind of go from one cyclic structure to the next, open up, close, and so forth. Basically what happens is in the sort of straight form of it, we will get sort of an attack. So for example here, if we had this guy, and I just make up one here, for example. And by the way, another thing that we did talk about, obviously, is this would be considered a D isomer, right? Because the last OH group there on the chirocarbon, furthest away from the aldehyde group or the ketone group, is on the right-hand side. And obviously, if it's on the left-hand side there, it would be an L. Again, as I mentioned, not 100% of the time, but fairly close to that. You usually could kind of back yourself up from the guy on the bottom there, that CH2OH group in a carbohydrate. And pretty much a lot of times that's going to be your last chirocarbon. Again, won't always be, but pretty close. That should be your last chirocarbon. So what we want to do is when we want to draw this guy into a ring structure, again, we want to number our carbons so we can kind of keep track of everything. Just like in organic chemistry, both the aldehyde group and the ketone group pretty much get the priority in terms of the lowest numbering. So this guy would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. And it really is up to you if you want to redraw it or just think about what happens. But sometimes people are taught, like we talked about last time, just to kind of take this guy and just drop it on its side. And if you take this guy and sort of drop it on its side, you could redraw it if you like. And 2, 3, 4, 5. And now when we do drop this on its side, pretty much everybody on the right-hand side is going to end up down. Or if you don't want to redraw it, all you have to remember is right-hand side down, basically. And everybody on the left-hand side will be up. And we can again number our carbons 1, 2, 3, 4, 5, and 6. And basically just put everybody back where they're at. So we have an H there, an OH, an OH, and an OH. And then obviously we have H, H, and OH. In this particular case, especially in a hexo situation like this, usually that 5th carbon, which is the chirocarbon, or if it's not maybe 6 carbons, then pretty much the last chirocarbon down the road is typically the one that will come in and sort of close this thing up as a ring. So again, this guy is going to come, and it's always going to attack wherever that carbon-oxygen double bond is located. And my recommendation is to do something like that. And what that allows you to do, once you sort of figure out what carbons are involved, you can just highlight them, circle them, whatever you want to do, but you can count them. And we got 1, 2, 3, 4, and 5 carbons. So understanding that tells you just that's the ring pretty much you're going to draw, because there's basically 5 carbons that are going to come together to make that ring. And that's where I would start with these drawings again, is that part of it. Now, one of the things that pretty much always happens when these guys kind of come into this cyclic structure is you'll have some guys that are kind of not part of the ring. And that is that carbon right there, carbon number 6. And that guy, for the most part, just to the left of the oxygen is always where it kind of ends up there on the ring. And that you could just kind of place up there on your picture to start with. That also gives you sort of a point to start numbering the rings so everything gets in the right spot. We know that that guy is carbon 6. We come down to the ring. That would be carbon 5. And here where we're numbering is we're going to go counterclockwise. So a good way to remember that is you can't cross the oxygen, and because it's not a carbon, right? If you go right, so you got to go to all the carbons to number them. And that's the way that you want to go. So that'll be 5, 4, 3, 2, and 1. Once you sort of have that set, you're pretty much good to go to finish out your structure. Once again, what happens here is this 5 and the carbon at number 1 basically is what kind of forms that ring. And what happens, by the way, is like this OH group comes in actually and attacks it. And that is sort of where the oxygen gets incorporated there. Is sort of where that oxygen comes from right there. And actually what happens through a process, you get a little hydrogen shift, and the hydrogen actually ends up over here. And that's that like last OH that you're going to put on the ring and stuff like that. So those guys are all in sort of forming the ring structure. So we do skip 5. We go to 4, and 4 is showing the OH down. So we draw a line going down. 3 is showing the OH down as well. And 2 is showing the OH going up. Again, on the other end of these lines are really hydrogens, but usually they're kind of left off so it doesn't get so crowded with stuff and in this picture. Now remember, sort of the last OH is really determined on what is sometimes referred to anomer that you draw. And there's really 2 types. There's either an alpha or a beta. And alpha pretty much means down, and beta kind of means up. So if we were going to draw the alpha version of this, we would put that last OH going down, and that would be our alpha. If we were going to do our beta, it basically would be the exact same structure. And again, everybody would end up in the same spot as we had over here. So down, down, and up. And the last one here would go up if this was beta. So again, they will basically kind of tell you, draw the alpha guy or draw the beta guy. So that will give you obviously a hint as to where you should put that last OH. Any questions on any of that? So definitely something you need to know how to do for sure. Yes. No. Yeah. Yeah.
So the one next to the O is not really on the line,
Which one now?
like the one that's alpha or beta.
Yeah.
On the right side. So that one is not on the.
Are we talking about this here or yeah? It is. It's attached right here to this carbon number 1, that line, if that's what we're asking. That OH is attached to this carbon right there. Yeah. The alpha just means that the OH that's there is going to go downward. And then here, this one's attached right there, and it'll go upward. Now, we saw one the other day, or we did one where, again, we had basically the other ring, and you can have a situation where you might have 2 carbon groups off of the ring. And in that case, you will have sort of that situation. So like, actually here, let's do this one. So if we had more like we had more of a ketone type of a carbohydrate, or really we could even have had a shorter one. So for example, if I just make up one like this, let's see if this will work here. So let's say we had this guy here just for fun, I suppose. Actually, for fun, why don't you draw it and see what you get? So draw that guy into a ring structure and see what you end up with. Then we'll talk about it. And why don't you draw let's do the beta of that thing. Okay, so again, in this particular case, we got carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5 only in this case. And in this case, what will happen is if we drop it on its side, we'll end up with maybe something like this. 2, 3, 4. Space there. And again, 1, 2, 3, 4, and 5. And here, everybody again to the right will go down. Everybody to the left will go up. So we'll have an H, an OH, and an H. OH, H, and then OH. In this case, it is going to be, again, that last chiral carbon down the road that's going to make the connection here. And that means we're going to get actually this move here. That, when we look at it, if we kind of count up our carbons, that's 1 carbon, 2 carbons, 3 carbons, and only 4 carbons in this particular one. So we're going to do this ring here, which is very much like cyclopentane type of ring. And again, just like normal, to the left of that oxygen, we're going to put that last kind of CH2OH, which in this case is number 5. Bringing it down here is 4, 3, 2, and 1 in this case. So we're going to skip number 4, obviously, as that's where how the ring comes to about. So we'll go to number 3 there. The OH is up. The OH is down there on 2, and here the OH would go up because it is beta here. So we did get this kind of shorter ring in this case because we actually had shorter number of carbons, or less number of carbons that we had in the last one, which was 6. Now, the last time we did one as well, I think we did something similar to this guy here. And on this case here, we actually have a ketone. And again, we would number towards the top to give that guy our smallest number. Here it would be number 5 that's going to go again here to our carbon-oxygen double bond. So it's always to that carbon-oxygen double bond. That's where everything sort of happens. And if we keep track of sort of how many carbons we need on this one, 1, 2, 3, and also 4. So this guy, like we kind of did last time, will also give us this kind of smaller ring, if you will. And I'll just draw it here. And once again, our number 6 guy in this case is going to go up here. And that would be 6, 5, 4, 3, 2. And I think the earlier question is, in this case, carbon number 1 is actually also off of the ring in this case. And that's what we see here. It is not part of the ring in this particular case. And that means that we still kind of do our same thing. I'm not going to redraw it here, but again, everybody on the right goes down and everybody on the left goes up. So we skip number 5, go number 4, and number 4 is on the right, which means the OH would go down if I got that carbonish. And number 3, the OH is to the left, which means it will go up. And this one would depend on which one you would want to draw. So if we did the alpha in this case, the alpha would mean that the OH would go down there on the first one. And then that is where we find our last sort of carbon group, which is carbon number 1 off of the actual ring in this particular case. So you definitely could have a carbon that's sort of off of the ring, and it usually will happen with this little sort of structure here. And, where you kind of have a smaller ring. I would say in the case of probably more like the cyclohexane ring, you usually will not have too much carbon off of the ring, but you definitely can in this type of situation. Or you could actually have everybody still on the ring like we had in the original one that we did as well. So it just sort of depends on the group. I would say that if you have a ketone group or a ketose, probably going to end up with 2 carbons off the ring like we did here in this last one. If you have more of an aldehyde group, you're probably going to have everybody onto the ring and no carbon off of the ring. Any questions on those there? Okay. All right, so as we were talking about here, this is again how this ring kind of closes up on itself. It makes this cyclic hemiacetal. Again, this is the OH on carbon number 5 there is kind of what we're looking at right there. And that OH is going to come in here and really attack the carbon. And again, the result of that is we actually will get this hydrogen here shifting out to the oxygen and the double bond and making that a single bond. And that is where we get the OH coming in and our oxygen. And if you remember, a hemiacetal is a carbon that has pretty much these components. It is a carbon that has directly attached to it an OH group, an oxygen carbon group, and a hydrogen. So that is your basically hemiacetal, sometimes referred to here as a cyclic hemiacetal because obviously it's in a ring type structure. And in terms of glucose, for example, this guy will basically open and close itself. But for the most of the time, it will be in sort of for glucose, the beta form there. 64% of the time, it will be in that beta form. And about 36% of the time, it'll be in the alpha form. And in between times, it will be there kind of opened up type of structure. So a lot of times it will close up. We'll make this sort of chain. And most of the time, we have a lot of beta D-glucose most of the time versus the alpha D-glucose. And here's kind of like the one we just did. Again, fructose here, which is one of those molecules you should be familiar with. Again, going to close the ring, as we just sort of did similar there, going to find it there, giving us 1, 2, 3, and 4 member ring, 1, 2, 3, 4 carbon ring, giving us again either our beta or D, which refers to basically that last carbon and where the OH group is located, either up or down versus the ring structure. All right, one last one there. Draw the cyclic form of this guy here. See what you come up with. Okay, so I'm going to number my carbons here. 1, 2, 3, 4, 5, and 6. I know in this case, we're going to go pretty much to our last chirocarbon, which oftentimes is one up there at number 5 in the hexose type of situation. That's going to go over here again to where the carbon-oxygen double bond is. Again, don't overcomplicate it. Just count some carbons at that point. 1, 2, 3, 4, and 5. So that is the ring I should draw. Remember that the 5-member ring is really like the cyclohexane ring that has that oxygen inserted inside. And as we know, our number 6 guy there is going to end up to the left of that oxygen, giving us 6, again, going counterclockwise here, 5, 4, 3, 2, and 1. Once again, I'm not going to redraw it. I'm just going to remember right-hand side down and left-hand side up. So we're going to skip number 5 and go to 4, and my OH here is on the left, which means I should put my OH up. We're going to go number 3, also on the left, which means my OH there will go up. We'll go number 2, which is on the right, which means my OH will go there. And again, this last OH going to be determined by what they asked you to draw. In this case, they want you to draw the alpha anomer. And that means down there is going to go my last one. Yeah. Any questions on that one there? So again, definitely something you need to know how to do for sure. Yes.
Question in regards to, so on the homework, they'll give you something like to meet like an alpha fructose, but how do you know what like the 2, 3, and 4? How do you know which side they would go on if it's what provided for you? Is it something you just have to memorize?
If what wasn't provided for you, I'm
So,
sorry.
like, if they just tell you like the name, right, this alpha galactose.
Okay.
And they say, okay, so you're gonna have to draw an alpha galactose, but they don't provide the fissure for you.
They don't provide the structure at all, is everything. Yeah, so you would, it would be, for our purposes, it would be provided for you. In the homework, you may have to go reference the book and stuff to find the original structure to start with, for sure. Yeah. But definitely on the final, it would be provided for you. So you would have a structure like that, and you would be asked to draw alpha or beta, hypothetically at the very top of the page. That's where you would do that on the final. Yes. Any questions on that there? Yeah. All right. Yeah. So definitely, like I said, the structures for the carbohydrates, there were some that I mentioned the other day that you do need to know, and you do need to be able to recognize it. You won't be asked to draw, the structure, just given the name, like the question like that, and to draw the structure. But if the structure was provided for you, you might need to be able to recognize it as glucose or fructose or something of that nature and stuff like that. But definitely for a problem like this, that would be provided for you, and you just got to put it together correctly. Other questions? All right. And hopefully that looks like what we do. I hope. All right, so let's talk a little bit about some of the chemical properties of monosaccharides. And monosaccharides are what are referred to as reducing sugars. And reducing sugars are monosaccharides with a carbonyl group that oxidizes to give us a carboxylic acid. So it basically, for the most part, again, is the same sort of oxidation we talked about with our aldehydes in organic chemistry. And, it's going to oxidize. That's the one where you kind of insert the oxygen there to our carboxylic acid. And it kind of works very similar here for our carbohydrates as well. And that's why they're referred to as reducing sugars, because they can get oxidized, right? So a reducing agent is something that can get oxidized. An oxidizing agent is something that can get reduced. So that's what this is referring to. They will undergo reaction with Benedict's reagent to give the corresponding carboxylic acid. That will give you a positive test, like we talked about when we were just talking about aldehydes being oxidized to a carboxylic acid, and we talked about the Tollens test and the Benedict's test. And because this will go through oxidation, it will basically reduce the copper here to the copper 1, and that's going to turn it from that bluish color to that kind of gross orangey color, reddish type color, and stuff like that, which would be a positive test. They include pretty much all monosaccharides: glucose, galactose, and fructose. Sucrose is one that will not, because it has something connected at a very important junction there on the first carbon, which will not allow it to sort of be a reducing sugar, but all the other ones will. We'll see sucrose in just a second, and we'll talk why that is in just a second. But here's the idea. Here's our glucose. And again, if we oxidize it with our Benedict's reagent, it will reduce our copper from copper 2 to copper 1. And again, really the only thing that's happening here, again, is the same oxidation that we see with aldehydes to ketones. And it's going to make basically a carboxylic acid group up there on top. And that would then obviously turn your Benedict's reagent positive in this case. And you can find some of that there in gums, right? The reduction of monosaccharides involves that carbonyl group. It produces sugars. They're sometimes found, as you can see there, in gum as well. So again, will be oxidized into that carboxylic acid. All right. So what would the product of this, not that you would necessarily have to draw it or anything like that, but really everything's going to be the same here, except it's going to get oxidized and pop that oxygen in there and make that carboxylic acid on top. Everything else will be basically the same structure underneath it. Not much is going to change, as you can see here in this particular case. And just so you know, even though they're carbohydrates, they're pretty much the same organic chemistry reactions we saw. That is an alcohol, right? Which, by the way, if you oxidize a primary alcohol there, you get an aldehyde. Then if you oxidize that aldehyde, you get a carboxylic acid. And if you reduce it, which is basically the backwards in all these, you get your aldehyde back and then your alcohol back. So although it looks a little different because there's a lot more stuff on there, it's really still that kind of functional group where all that oxidation and stuff occurs. And it's the same sort of oxidation pattern that we saw with alcohols to aldehydes to carboxylic acids and back. So let's talk a little bit about disaccharides, a little cheese and milk to go with our bread that we've been talking about. So as I mentioned before, disaccharides are di meaning two. So they're basically two monosaccharides that have been put together. And they have been put together by removing water. So basically by removing water, they get stuck together. And these are three monosaccharides that you do need to know. We're going to look at each of them separately in just a second. But you do need to know all three of these: maltose, lactose, and sucrose. And more importantly, you do need to know the monosaccharides that make each of those up. And so, for example, maltose is basically made up of two glucose molecules. Basically, take water out of those two glucose molecules and stick them together. Lactose is made from a glucose molecule and a galactose molecule. And sucrose is made from a glucose and a fructose molecule. And again, each of those are taking out water. As we talked about, as we'll see as well, if you wanted to go backwards from the disaccharide back into the monosaccharide, you basically just add the water back in, and it will break those guys apart into their individual units. It'll break it back into, say, two glucoses, a glucose and a galactose, a glucose and a fructose. So take a look at each of these a little bit more and just briefly here and talk about what is going on here. And maltose, first off, is a disaccharide. It's known as malt sugar. It is composed, as I mentioned, of two D-glucose molecules. It's obtained from the hydrolysis of starch. And another thing that you need to know in terms of the carbohydrates are the type of linkages there are between the different carbohydrates. And these are what are sometimes referred to as glycosidic bonds. And depending on the type of linkage that you have, you'll have some different glycosidic bonds. And this particular one is linked through what is referred to as an alpha 1,4 glycosidic bond. And we'll take a look at it in just a second. But basically, the name is a description of where the bonding's happening. So it's happening on the alpha OH, which, as we know, alpha is down. So it's that carbon on number one that's putting down the OH. And that is on carbon number one. And it's actually on the OH on carbon number 4 is where the other attachment occurs. This is what's used in cereal, candies, and brewing. It can happen in both or be found in both alpha and beta forms. So let's take a look at it to sort of show you here. So these are two alpha D glucose molecules. They are alpha D glucose because at the carbon number 1 spot, the OH are going down, basically, right? So what's going to happen here is they're going to join through what is referred to as an alpha 1,4 glycosidic bond. So what does that mean? We are going to take water out. So we're going to remove water. And really, it's up to you, however you want to think how water comes out. But we're basically going to remove an OH and an H. So that's going to come out. And that's going to be the water that's going to be lost between those two to allow these guys to come out. When they come out, what is left to join the two sugars is that oxygen. So this oxygen is what is left that's going to bind. And it will make this bond here with that oxygen. And that bond there is what is referred to as alpha 1,4 glycosidic bond. Alpha means down. If you look at that bond, it is kind of like going downward, right? It's kind of heading in a downward direction. That's a good way to remember the alpha part of it. The numbering is literally the numbering of the carbons of where it's coming from. So we go backwards, right? 6, 5, 4, 3, 2, and 1. So that is where the 1 comes from. That's the guy involved in the bond. On this guy, this is 6, 5, and 4, just like we were doing. And that is where the 4 comes from. So the two numbers indicate the carbon where the OHs are coming together to make this bond. So that is what is meant by alpha 1,4 glycosidic bond. This is the classic looking of that bond. And the way you can remember, if you see like a bond coming down with an oxygen in the middle, you're probably looking at an alpha 1,4 bond, as long as that bond is originating at carbon 1 and carbon 4, where they're going to come together. So that is definitely the way to remember this. So you do need to know how to identify that bond if you see it as an alpha 1,4 glycosidic bond, and also know that that is the bond that is in maltose, which is made up here of 2 glucose molecules. So maltose made up of 2 glucose molecules held together by an alpha 1,4 glycosidic bond. Any questions on that there? Now, the next type of disaccharide is our friend lactose. Friend for most, maybe not all. That is cheese and milk there. And it is a disaccharide that's made up of beta D-galactose or alpha or beta glucose. So basically a galactose and a glucose is going to put these together. Now, when we have this here, our galactose is beta, which is upwards, right? That's what beta means, going up. And here, this is going down, and that is our alpha on this end here. Remember, it's carbon number 1. We determine alpha on there. So in this case, same thing's going to happen. We're going to take out water, just like we kind of did before. And however you want to do that, you could take out that and an H there, and that's going to give you your sort of water there that you have, maybe. Now, what we're going to do is put it together. Now, this location here is going to be a little bit different in terms of how it's going to come together. And it's going to come together in what is referred to as a beta 1,4 glycosidic bond. Now, beta means up, right? So if you remember, we just saw alpha, which it kind of looked like the bond was going down. This guy kind of looks like it is going upwards, yes, in that sort of direction, heading up. And that's a good way to remember that this is going to be a beta bond rather than obviously this one coming downward in a V. So it's the same idea. It's beta 1 for where the connection is happening, 5, 4, 3, 2, and 1. And on the other guy, it is 6, 5, and again, 4 in this case. So we have our beta 1,4 connection here. And that is definitely a different looking bond than you see with your alpha 1,4 connection there. So again, you do need to be able to recognize this bond as well if you see it. You also need to know that is the bond that we find here in lactose. And you also need to know that lactose is made up of galactose and glucose. Yes. People have trouble with that bond. Yes. And lactose intolerances and processing that in the body. The next one is sugar, which is sucrose. And sucrose is obtained from basically a glucose and a fructose. And this has a much different sort of connection than the other two. And you can definitely see the difference in the connection here when we look at it. And if we come down here, here it is. We have on our glucose our 6, 5, 4, 3, 2, and 1. And that is alpha D-glucose. And here on our fructose, we have our 6, 5, 4, 3, and 2 there. And here we do have our last carbon off of the ring, right? So we have that guy where we have it off of the ring, and that would be carbon number 1. And that's beta fructose. So because the connection here is actually, if I just draw the end part of both of these, we basically have, this is sort of what it looks like before. And here we go like this. So this is carbon 1 on both of those. This is our glucose. And this is our fructose, just the carbon 1 side of it. Here the connection is actually at the alpha or beta carbon on both of them. And this is why we see both descriptions there, alpha and beta On the previous ones, we had just alpha or beta, and that is because on the previous ones, we only involved one of those alpha carbons or beta carbons. And on the previous one as well, for our maltose, we also only involved one of those sort of alpha or beta carbons, carbon number 1. In this case, we have both of those sort of carbon number 1 or alpha carbons, really carbon 1 and 2 in this case. But because they are both involved, really, that is why we have both of the descriptions here. So we have the alpha for our alpha glucose, and we have the beta connection. And once again, here we're going to remove water from these two guys, and we're going to get rid of water. And that is where our connection is going to happen. This one is definitely different than the previous two looking, because this one pretty much looks straight down. Yeah. So this guy's going straight down again from carbon number 1 up here to carbon number 2 down here. And that's what gives us our alpha, beta, like the old supermarket 1,2 glycosidic bond. Anyone? I can still use that reference. That's good. I'm not that old yet, I suppose. That's good. Glycosidic bond. If you're not sure, that was a supermarket years ago, alpha, beta. Now I think it's food for less, I think is where they eventually ran into and became, but there used to be alpha, beta. I know. All right, so here is the alpha, beta 1,2 glycosidic bond. I'm not lying to you. You could Google it. It's true. Just go shopping there all the time at alpha, beta. So this one, again, looks different than the other two. This is, again, kind of a straightforward, and that's because they have to line themselves up with those 1 carbons or the N carbon kind of on top of each other. And that gives you that alpha, beta 1,2 glycosidic bond. So for sucrose, you do need to know, obviously, it's made out of a glucose molecule and a fructose molecule. It has this alpha, beta 1,2 glycosidic bond. And this is also why earlier we talked about it not perhaps being a reducing sugar. And that is because it's missing some vital hydrogens over here on those carbons because they're involving in that bond and stuff. Is it true? It is. Yeah, and they merged. I think they became like food for less, I think, and that's where they ended up going and stuff. But yeah. All right, so I probably was alive then, I imagine, if that was when it happened. All right, any questions on that there? Okay. One day I'm going to say that and nobody's going to know what I'm talking about. Yeah, that sounds good. I know I'm almost there. It's all right. So if we wanted to break apart any of these disaccharides at this point, what we're going to do is basically we can just add the water back. So here's our sucrose. And much like anything else, it would break apart, where that oxygen sort of holds both of those guys together. And basically what you would do is clearly just get back your OHs on each of those. So you would divide up water, and obviously wherever you want to send this oxygen to, it would need a hydrogen. The other guy would need the OH, and you would get back your monosaccharides there. So again, to put them together, we take the water out, and obviously we could do a hydrolysis and add water to break them back apart into their individual molecules there. All right, artificial sweeteners, they're sweet. All right, so take a moment here, and which ones are in each of these? You do need to know these, perhaps. Yes, for sure, maybe, possibly. I'm almost sure of it. This might be a really good thing to know, I suppose. All right, so lactose made up of lactose, glucose. Well, is there more to that there? All right, so again, we have glucose and galactose. There we go. Our maltose is made up of a couple of glucoses, right? A couple of those guys would do it, yes. And sucrose is made up of our glucose and fructose. Definitely, I would say something you should know for sure, yeah. And also, again, the glycosidic bonds, being able to identify them. You probably won't be asked to draw them or anything like that, but if you see them, to be able to identify them correctly with the numbering and stuff like that. Any questions on that there? All right, so let's talk about polysaccharides. Polysaccharides are pretty much just a bunch of glucose molecules stuck together. Bunch of them where we basically pretty much just remove water between each of them and put them together. So they are polymers, which are really large sort of molecules. They include amyloase and amylopectin starches that are made from alpha D glucose. They also include glycogen, which is animal starch in the muscle. It's also where we store everything, right? Glucose and all that stuff for later use through gluconeogenesis and break it back down. They include cellulose, which are plants, and wood, which is actually beta D glucose. So let's take a look at each of these potatoes. Maybe we'll see them tomorrow. I don't know, maybe, possibly. So we have amyloase here, which is on the bottom, and they have our characteristic looking bond that we saw earlier, which again you could see going downward here pretty much. So that's going to be our alpha 1,4 glycosidic bond. Amylose is pretty much a bunch of D-glucoses. It is basically unbranched. So like in organic chemistry, branches mean things go off the sides. This is just a straight run of taking out water and making basically that alpha 1,4 glycosidic bond all the way through. Amylopectin is pretty much similar to it. It has that big run of glucoses straight out with each other. Also has the alpha 1,4 bond, but it also has at some point some branches that occur. So this branching actually gives us a different looking bond. So let's just see how we get to this bond name. This is alpha 1,6. So it means the same thing. Here is the alpha carbon there on that guy, and that is number 1. So that is where the alpha 1 comes from. Here it's actually attaching to carbon number 6, that kind of CH2OH off of the ring. So that is where the 6 comes from here. And again, you could kind of look at it as coming down, I guess. So that's alpha 1,6. Here we do not have both alpha and beta because the connection here is to carbon number 6. And it's not like the carbon 1 to 1 or 1 to 2 connection like we had with that alpha beta one that kind of looks similar to that. Here, this is just alpha because it only involves that guy up there on top. Only involves that one alpha carbon. This is not an alpha or beta carbon. So that's why, again, there's no beta with it or anything like that in terms of this name. So again, remember the name's pretty much like an organic. It's just all about location, telling people where things are at. And that's what the numbers represent, is where that bond formation is basically happening. And again, for the most part, you could kind of figure out if it's alpha or beta, depending on sort of the connection and how it looks. So amylose, like I said, is that straight chain linked through that alpha 1,4 glycosidic bond. It is continuous. It is unbranched. And then our amylopectin, again, has those 2 bonds, one where we have the straight, and every so often we get these sort of branches that come off. And then it kind of continues out the same way. It kind of continues with kind of that straight alpha 1,4 bonding that's happening. Glycogen, which is a polysaccharide, and that is basically, again, where glucose is sort of stored. Again, if you go through glycolysis, it's got a little leftover glucose there, you store it. And then, like I said, you can use it as energy stores later on through gluconeogenesis, break it back down, and use it for some energy. It is similar to amylopectin, but it's way more branched. So it's got kind of the same bonds as the amylopectin, but there's a lot more branches happening there with glycogen because it's kind of put together to store itself. So a lot more branch points happening, but it basically has the same bonds that you see with the amylopectin, just a lot more of those branches happening. Cellulose is a polysaccharide of glucose, and it has the beta 1,4 bond. Once again, as we saw earlier, you could kind of feel like it's going upwards there. And again, that should give you the beta idea there. And it's still the 1,4 because I'll just look at this one. That is carbon 1 on this guy. And again, 6, 5, and 4 on that guy. And again, it's going upwards. And that's where the beta 1,4 connection basically comes from here. Cannot be digested by humans, so you probably shouldn't eat it, I suppose, and break that down. We can't really break down that beta 1,4 bond. That's not so good for us. All right. So, oops. Identify the polysaccharides and the type of bonds that are happening in each of these here. So if we take a look at it like we just saw, we have our cellulose, which has our beta 1,4. And that's the one, again, going upwards. Don't eat it. Can't digest it. Amyloids and amylopectin there in our baked potatoes there. We've got some alpha 1,4, straight chain for the first one there. Again, we have a slightly branched chain happening with an alpha 1,6 and an alpha 1,4 for the straight part of it. And then glycogen, as I mentioned before, has basically the same bonds. Again, just a lot more sort of branches. So again, you do need to be able to recognize these and just, for the most part, you see something like that, probably going to be an alpha type of deal. You see kind of like that move is probably going to be a beta. You see this move, and again, it's at those sort of end carbons on each of them. You'll probably have like an alpha beta type of situation. If you see this move and it's only at one of the end carbons and not at the other end carbon, then you might just have an alpha type of thing. So again, those are how you want to kind of think about those visually. They'll kind of help you sort of figure it out. And then don't get hung up on the numbers. It really is just number the ring like you were drawing it yourself, going counterclockwise, and you can identify where that connection is happening and what the numbers would be. Any questions on that there? All right. Well, that's chemistry for the season, I think. Yes. Any